Hello and welcome back to another video of Bare Metal C. In this video, we want to implement PWM or pulse width modulation. Now, in the last video, we created this circuit, which is made of two potentiometers and this button, which simply activates this blue LED. And every time we press it, it prints out "Hello World." Now, what we want to do is that since we know that for this first potentiometer, it actually varies the blink duration. So you see how I'm turning this potentiometer, the LED blinks more and more often. So if I turn it this way, you see it blinks more rapidly. And when I turn it all the way clockwise, it turns on for 1 second, it'll turn off for 1 second. So I also did change the code to blink every second instead of blinking every 5 seconds. So that is a modification I made. I'll show you that later. And so I want to have such that this this potentiometer varies the brightness of this green LED. So I'm going to lower the brightness on the camera, and I'm going to lower the brightness of the LED now, and you'll be able to see. So I'm going to blink this LED a bit faster, so you can see that it's varying in brightness. And I'm going to lower the brightness. You see that? It's very, very dim now. Look, now it's completely off. And when I turn a bit, it's back on. I slowly will turn it back clockwise. The brightness increases, and it's at full brightness now. Okay? So that's what we want to achieve, and we'll do that by implementing PWM. I'll first talk to you about what is PWM, and I'll try to break it down as much as I can. And I'm going to do that by showing you a little chart I made. So PWM stands for pulse width modulation. Okay. So we are essentially changing the width of the rectangular pulses. So that's how the pulse width modulation works. Now, what we are usually used to is a regular digital high and low. So we have high, which is 5 volts, and low, which is 0 volts. And for high, we see that the brightness is simply on, right? So the LED is simply on. And for low, it's simply off, so 0 volts. Now with pulse width modulation, what we can do is we can turn on and off this LED so fast that it will actually look like it's between 0 and 5 volts. We see that on over here, I can actually vary the width of this rectangular pulse, and let's say it's 70%, right? So what does that mean? So 70% is the duration or the width from the total period, right? The total period is from here to here, okay? That's 100%. And as you vary that, you'll actually get the brightness that you need for your LED. Now, there are different types of pulse width modulation. There is phase corrected and there's fast PWM. In this video specifically, we'll only go over the topic of fast PWM since we just want to control the brightness of an LED. And I'll go over phase corrected in a separate video. So fast PWM we'll use to change the brightness of an LED, and we'll do that by changing what we call the duty cycle. Now, 0 here is just 0 volts, and 255 is 5 volts or digital high. So we can see that I put a line here and I put an arrow to it and it says average voltage. Now, the average voltage is the peak voltage multiplied by the duty cycle. And the duty cycle is the percentage of time the signal is on. So in this case, it's 70%, right? Or in this case, it's 10%. And if you multiply the peak voltage by the duty cycle, which is this here, you'll get the average voltage, which is here. And that average voltage is what we will emulate when we get, for example, a lower brightness on the LED. All right. So the switching frequency is 1 over the change. So the period, which is from any peak to peak. So from here to here is one period, and 1 over that is your switching frequency. So we control the amount of power delivered to a device, and so we control the behavior of the device. Okay, so that's how that works. Now on the Arduino, we have different timers which can have different behaviors, which I'll get into also later. Okay, so this diagram looks a little complicated at first, but it really isn't too bad. So here we see that we have this triangle, right? We have this triangle that goes up, down, up, down. It's repetitive, okay? Now this is what happens in Fast PWM. You essentially have something that is counting from 0 to 255, and depending on what you put as your flag, which is made by these little blue dots here, is what the brightness of that LED will be. So this flag is also called OCR register, which is the output compare register. Essentially compares that current value from this register to where the counter is counting at. So it'll automatically count from 0 to 255, and whatever you set this will mimic, or sorry, will create the PWM signal that you want. So let's say we start from here, right? We start from 0 and we set OCR NX, or OCR timer, let's say 0, or yeah, timer 0, or to group A. So that's what the N and X mean. We say that, okay, we will count from 0 and then we'll go up to 255. Let's say that we set OCR to 127, so about around half of 255. So what'll happen is that from 0, it'll be high. So we see that it's at 5 volts. And then it'll go up. And since we set it to 127, over here, it's going to, oh, you see, it's going to be equal to this, and it's going to go back to low. And it's going to stay low from OCR all the way to 255. At 255, it'll overflow and it'll go back to 0. And so since it's from 0, it's going to go back to 5 volts. It's going to stay at 5 volts until whatever flag you set it at, and it's going to go back to 0 volts. So it's going to keep doing this. And depending on where you set this flag, it'll change the brightness of the LED to your needs. So here, let's say it's around 200. Well, you'll see that it's going to be like a good 80-90%. So it's going to stay high for most of that duration, and it's going to go low for whatever remains from the flag to the top. So that's how this works. So this is sort of the timing diagram of Fast PWM on the Arduino. Now, I've also made lines covering the average voltage, which I made by putting some purple dots. So here, since it's around halfway, the flag, the voltage will also be around half, okay? And here, it's slightly more than half, so I just made some dots a bit higher than half. Here, it's much, much higher, so it's almost full brightness. So it's somewhat like, let's say, 4.8 volts, and it goes back down. And for this period of time, you see that it's very, very low, so it's going to be close to 0, not quite 0. And then this last flag is all the way at 255, so it's maximum brightness for that whole period, so it's 5 volts. So you can see that if your flag is set to 255, well then for this whole line over here, it's going to be 5 volts, so your LED will just look like it's digital high. Just like I said before, we have our timing diagram, and our timing diagram from before was in non-inverting mode. Now, what is non-inverting mode? Non-inverting mode means that from the value 0 all the way to the value of the flag, it's going to be high. So it's going to be 5 volts. And from the flag all the way to 255, or also known as top, it's going to be low. So it's going to be 0. So this is a very common setting that we turn on in order to enable fast PWM. And we turn this on by modifying the waveform generation mode registers. Now, inverting mode is simply the opposite. So from 0 to OCR, it's going to be low, and from OCR to top, it's going to be high. That's it. Now, there's something very, very important when it comes to timers, and that's that depending on the timer, either 0, 1, or 2. So you can set, let's say, timer 0 as PWM. That means that for timer 0, you have group A and group B. Both have to be PWM. You cannot have one for timer or like a counter and the other as PWM. So remember how in the system setting, we defined timer 0, I believe, as our counter. That means that for any other group inside of timer 0, so group A or group B, we cannot use it as PWM. It's set as a counter. But since timer 1 and timer 2 are still free, right, since we didn't initialize those yet, it's important to note that we can use those as PWM. Okay, so it's just a reminder that you can only choose one configuration per timer. Now, timers also have resolutions, right? I mean, from PWM, for PWM, we have 8-bit, 9-bit, 10-bit, and even 16-bit. So the most common one is the 2 to the 8 or the 8-bit timer, which goes from 0 to 255. And that represents our duty cycles. So it'll be from 0 to 255. And so that means that we have 256 steps. And as we increase the bit, the number of steps also increase. And that means that we have a higher resolution as we increase the number of bits on that, let's say, PWM. So when will we be using different bits? So if there isn't any precision involved in the task that we need, so for example, the brightness of an LED doesn't really need high precision, we can simply stick with 8 bits. Okay, so that's a duty cycle that ranges from 0 to 255, which gives us 256 steps we can control for the brightness of that LED. Now, this is considered the lowest resolution that we can have, and we can use the brightness of an LED on an 8-bit, 9-bit, or 10-bit value, or PWM. But what about 16-bit? So 16-bit, it means that we need it for tasks that have a very high amount of control, that require high amounts of control. And so things like quality servos, audio processing, precision motors, especially like in the medical field where you have like the Da Vinci, right? Where you have different motors that require extreme precision, or even 3D printers, which require, you know, a 10th or even 100th millimeter precision accuracy, and displays. So if you have a really big display or an OLED display, you may need high precision for the different brightnesses. But for an 8-bit, it can be used to control, like, say, LEDs or even fan speeds on your computer that you're using right now. Like 56% fan speed or 55% fan speed doesn't really matter, then you can always stick with the lowest one. So it's really important to know what bit PWM resolution you want depending on your task. Let's go ahead with the code. All right, so we're back in the code. And before I just get into this, I just want to say that I've actually switched over to Linux, and I'm actually really happy about this change. I'm still getting used to it, but maybe I'll make a separate video. I know this is kind of off topic, but I'm very happy with this change. It's definitely it's less bloated than Windows. So I think from now on, I'll just stick with Linux. And this also means that I'll have to do some modifications with some software I've developed that was exclusively with Windows. So those who are Linux enjoyers, then I'll probably be making a Linux version of the Cosmic Tower. So I might make a separate video on my Linux setup and what I've got going on. I'm using Mint as my distro, but yeah, that's about it. Let's go back to the code. Let's make our PWM initialization. So we'll go here on the source, create a new file, and we'll call it pwm.c. Okay. And in pwm.c, we'll actually just come here and go to the main, and we'll copy these standard libraries, including the AVR libraries, and we'll just paste it up here. And up here, what we'll do is we'll have to create our initialization file, right? We have to create our void, which is going to called pwm init. So this is the order of the tasks we'll have to complete. The first one is to have it in non-inverting mode. The second is our waveform generation mode, which will have to set to Fast PWM. And the last one is our prescaler. So let's start with the first one. So if I go over here, I'm in the data sheet of our Atmega 328P. And to have it in non-inverting mode, I'll bring your focus to table 15-3. And here it says compare output mode, fast PWM. And in here, if we look in this section, it says clear OC1A on compare match, and then set OC1A at bottom, non-inverting mode. So it clearly states that this is non-inverting mode, and we have to switch this bit to high. And this bit is located here in timer counter control register A. And it's bit number 7. So we'll bring this to the side and we'll access this register, and then we'll set that to high. So that's all. So all we've done is set non-inverting mode. So that's complete. The next one is our WGM, and we have to place it in fast PWM mode. So if I go here in this table, so this is table 15-5, waveform generation mode, bit description. Here, mode number 1, mode 0, 1, 2, 3, 4, 5, all the way to mode 15. And here we start with normal, then phase correct with 8-bit, 9-bit, 10-bit, CTC, and then we have fast PWM explicitly in 8-bit. And to actually set it to this, we have to set 2 bits to high. The first one is WGM 12, and WGM 12 is located on register timer counter 1, control register B. And if we look through it and scan through it, we can see that it's actually bit number 3. So bit number 3 has to be set to high. So we'll access this register, and I'll set that bit to high. Okay. But we also had another bit that we had to set to high in order to achieve fast mode. And that is specifically WGM10. WGM10 is not located in this register, but it's actually located up here in register A. And in register A, we can see that it's specifically bit number 0. So bit number 0 has to be set to high. So I'll bring this to the side and make it an OR operation up here. So it's a bitwise OR, and I'll set WGM10 to high. How about our prescaler? Our prescaler will bring our 16 megahertz frequency down to a specific divisor. In this case, we have the options of 1, 8, 64, 256, and 1024. We'll choose a prescaler with divisor 8, and this is only CS11 set to high. So this is our bit set to high. CS11 is located here in register B, and so that's bit number 1. So I'll go here, I'll make a bitwise OR, and I'll say 1 CS11. And that's it for the initialization of our PWM. The next thing I'll do is another void. And here I'm going to say LED underscore LED brightness. Okay, so this is where we'll actually change that register, LED brightness, and we'll pass an unsigned 8-bit integer, and we're going to call that brightness. And in here, what I'll do is I'll simply set OCR1A to brightness. Now, where did I get OCR1A from? That's the pin that we'll actually be using as our PWM. So here, OC1A is PB1, which is our green LED. And putting an R between the C and the 1 just gives us access to that register. So that's it for our PWM initialization. We'll go here and create our header file, pwm.h, and we'll just say if it's not defined, then define it. And then at the end, we'll just write and if. Here, we're going to include our standard library for integers. We'll also create our void. So this is where we just initialize these functions. So we had PWM, init, and as well as LED brightness. And that's it. So we had 2 functions in total. Now that we set up these 2 files, we'll go to the main and we'll simply include our header file. Then we'll go to our setup, and down right here, we'll say PWM underscore init. And then here we have to do brightness. And we'll set it equal to a pot value. Okay. Now brightness is not initialized, so I'll just go up here and just write unsigned 8-bit integer and just call it brightness. And I'll initialize it to 0. Here, what I'll do, I made a little typo, is we'll have to actually create our curve just like our ADC from last time. And speaking of our curve from last time, here I just set it to pot val 0 just to keep things simple. And this sets it to blink duration of 1 second. So last time we did all that calculation for 5 seconds, but I think it's just simple to keep it at 1 second blink periods. And I also made these clampings in order to simply set it to 1 second if the pot value is above 1,000 and 0 if it's less than 20. However, for our brightness, we can't simply set it to our pot value. So we'll have to actually create our equation for our line. So I'll go back here, and very similarly to last video, on the y-axis, we have our pot value. And on the x, we have the brightness, which spans from 0 to 255. And this is a linear line, which starts from the origin. That means that our y-intercept b is going to be equal to 0. Isolating for x, since that's what we actually want, and that's our variable called brightness in our code. this is equal to our y divided by m, which was our slope. Doing that gives us 255 divided by 1023 multiplied by pot value. Now, you can't simply do this in the C code because integer divisions, this will result in 0. This will cause some problems. So what we'll have to do is we'll have to assign this as an unsigned long and then do the division and then set it into our X value. And it's quite simple when you want to do things like that. So I'll go back to the code. And here what we'll do is we'll create a parentheses 255. And just like before, when I said unsigned long, I'll do UL. So both capital. This just makes 255 an unsigned long. And then I'll multiply it by the pot value 1. Then I'll divide it by 1023. Now this gives exactly the line that I showed a few seconds ago. Okay, so we have that set up. Now what? So we want to change the brightness of the LED. Now what this line does simply turns on the LED and then off every second. But we don't want that. We need to change that brightness. We need to change that brightness depending on the pot value. So I'll go ahead and simply delete this. And we have to create a Boolean state for our LED. So what I'll do is I'll go back up here and below this Boolean, I'll create a static Boolean, and I'll call it LED state. And I'll set this equal to false. Okay, so initially we'll just say that the LED is off. Going back down here, I'll say if the LED state is, let's say, on. So let's say the LED state is on. So this means that it's true. We'll actually call LED brightness and turn it off. Then here, otherwise, right? So if this is false, then we'll do LED brightness is equal to brightness that we've defined up here. Now, just like our exclusive OR, it would keep switching between on and off. So what we'll do is we'll set LED state is equal to exclamation point LED state. So we've essentially, what we've done is we've negated this Boolean value so that every time it passes through this function, it flips between true and false. So we are mimicking our exclusive OR that we've done here. And all we're doing is we're setting different brightness levels depending on what the LED state is. And then we'll also just keep our last blink time is equal to current blink time. So what we'll do is we'll upload this code and we will see what this gives us. So I'll press upload and switch cameras. I'll bring this down. There you go. So it's still blinking. And I'll just turn this knob all the way down. And you see it's very, very dim. You see it's like very, very dim. And I'm going to bring it all the way this way. There you go. This is maximum brightness. I'll bring it halfway. That's half brightness. It looks much brighter on camera due to the camera settings. But I'll just bring it a little bit lower so you can really see that it is changing in brightness. There you go. So it's a little there, little increments. Okay, so initially it looks like it's working properly, but there is one problem with this. Notice how whenever the LED is supposed to be quote unquote off, there is a slight light going through the LED. So it's not completely off right there, right? Whenever the LED is supposedly off, there's still a little bit of light seeping through. So what do we do there? Well, since the grounding is not perfect and, you know, the PWM always lets a little bit of voltage in, we actually have to turn off the PWM whenever the brightness that we pass through LED function is 0. So whenever this is 0, we have to go here and create a sort of logic to completely turn off the PWM. So I'll show you how to do that right now. So here, let's say if the brightness that we pass through here is 0, then we are going to actually turn off this specific bit from this register. So what does that mean? That means, right, we're going to do TCC R1A. And since we don't want to turn off all the values in this register, we just want to turn off this in the register. So this means that we have to do a bitwise AND operation. Okay, so we have to do AND is equal to tilde 1, COM1A1. What we'll also do is completely turn off port B with also the AND operation. So this is PB1. Otherwise, if the value passed through here is not 0 or non-zero, then we'll just put this here. And above it, I'll just take this value and simply make it a bitwise OR operation. So we turn on this specific bit once more. So let's see if that's all that is required when doing this. So we'll go back to the main and I'm going to upload this. I'm going to switch cameras. And look at that. Now, whenever it's supposedly off, it is off. Now, if you want your potentiometer to be completely turning off the LED when it's completely counterclockwise, well, we can do that with a simple clamp in our main function. So I'll go to here and right below the blink duration clamps, I'll go here and write, hey, if our pot value for this potentiometer is less than or equal to 20, then let's have our brightness set to 0. And if our potentiometer value is greater than or equal to 1000, then I want it to be at full brightness. So that's 255. And that's all you need, right? So now if I upload this, go here in the camera, you see, it's not blinking anymore. Everything is working, as you can see, but I have to still turn this potentiometer. There you go. Now it's slowly increasing in the brightness, and I can turn it until it's maximum. So in this video, we've successfully implemented PWM. I think I've gone pretty in depth in Fast PWM. I've gone through the data sheets. I've explained, the timing diagrams, and we were able to successfully implement 2 potentiometers controlling a single LED's behavior. And for the next few videos, I think I'll also still be focusing a lot on ADC and PWM. And then after that, I'll probably be entering protocols. So thanks for watching. I hope you enjoyed. Comment down below what you thought, like, subscribe, and I hope you have a good day. Take care.